Hello everyone, this is Arash Jahangiri from Virginia Tech. So today is the fourth of six webinar sponsored by MAUTC and VDOT. Today we're going to have two presentations. The first topic is winter weather demand, and the second one is alternative intersection analysis. So you have three options for audio connection. First is using VoIP, which is basically your computer speakers. The second one is having the audio system call you. In that case, you need to type in your phone number at the prompt. If you can see on the right, the window on the right shows that if you choose this option, you need to type the number. And the third option is dial into the teleconference. If you choose that option, there are more information will pop up, like the phone number that you need to call, and also a PIN code, which will be asked later. So there are several ways to increase the interactivity. First, you can type questions and comments in the chat box on the left side of your screen. Also, after each presentation, we have discussion time. So we'll try to address all questions before moving on to the next speaker. Also, there will be several polls for each presentation, and also some speakers may ask questions. In that case, you can answer the questions through the chat box on the left. So as probably you know, MAUTC stands for Mid-Atlantic University Transportation Center, which is a consortium of 6 universities led by Penn State University, along with University of Virginia, Virginia Tech, Morgan State University, West Virginia University, and University of Maryland. This webinar is a tech transfer project. It's a joint effort by the University of Virginia and Virginia Tech with additional support from Virginia VDOT. And the purpose is to disseminate webinars of MAUTC projects at the two universities. And these webinars are held the second Thursday in the month at 2 p.m. Here are the two remaining webinars. As you can see, the next webinar is going to be on November 13th from the University of Virginia, and the last one is going to be on December 11th. If you would like, we can issue a certificate for your attendance for these webinars. So if you want, please email your request to Dr. Ihab El-Shawarbi at this email by Monday, October 13th. Also, the presentations can be accessed through this link. If you go to the website of the Center for Transportation Studies at University of Virginia, you should be able to find major programs and MAUTC, and from there you can find the presentations. So I'll give you maybe 1 minute if you want to write a note, maybe the email. So the email that you need to send your request is shawarbi@vt.edu, and you need to send your request by Monday, October 13th. All right, so here's the first poll. So who are you? There are multiple choices that you can choose. If you're local government, other government, university students, or university faculty. So moving on to the next poll, that's how many people are being with you.
you are using your laptop, just say yourself. Just you. If you are using your laptop, you're just you. I'm taking for the others.
So moving on to the next poll. So how familiar are you with winter weather demand? This is the first topic of the presentation. So moving on to the next poll. So how familiar are you with the alternative intersection design? This is the topic of the second presentation. All right. So today's webinar, as I said, includes two topics. The first topic is winter weather demand considerations by Dr. Pamela Murray-Tuite from Virginia Tech. Then we're going to have a discussion time. And the second topic is development of methodologies for alternative intersection analysis by Dr. Hesham, Rakha, and John Sangster from Virginia Tech. And then after, we're going to have the second discussion time. So I will let the first speaker, Hesham, to start her presentation. She's joining us from Northern Virginia.
Great. Thank you, Arash, and thank you, everyone, for attending. This project actually was conveniently delayed in the survey that we did because we had trouble getting the survey deployed. But we couldn't have asked for really a better winter to conduct a winter weather survey than this past one. So for terms of the presentation outline, we'll give you some brief introduction and background, briefly discuss our survey methodology and some of the data that we collected, and then get into some of the modeling results and some conclusions that we can draw from our study. So the 2013 and 2014 winter was particularly harsh for the U.S. East Coast, as I'm sure you will remember if you happen to have been here. And if you think, even Atlanta, Georgia was experiencing winter weather, and their kind of surprised weather ended up giving them basically a no-notice evacuation in a snowstorm. So that you can see that then understanding what's going to happen with winter weather demand is fairly important, right? Because you don't want people to be stuck in their cars in the middle of a snowstorm. And in this winter, we had snowstorms, we had below freezing temperatures that were disrupting the school and employer schedules, as well as the road operations. So the goal of our work was to examine the winter weather effects on demand so that we could better understand the complexities associated with winter weather travel decisions. And as an, sorry. As an example, taking the Fairfax County public school system as a sample of the closures and delayed openings that were experienced in Northern Virginia, we had 11 days of closure due to winter weather this year and 9 delayed openings. So this caused a lot of disruption to to daily travel. And you can see, for example, at times we're closed for almost the entire week, right? So the January 21st to 23rd, for example, that's a Tuesday through a Thursday, but we already had Monday off due to Martin Luther Day. So we ended up with a partial day on Friday as the only day that schools were open during that entire week, right? And so also some of the employers were disrupted as well. Okay. So just to see if you were around during this past winter, I put together this poll question to see if your travel was affected. Okay, great, thanks. So it looks like the vast majority of you have had some disrupted travel in the last year because of the winter weather. And if we look briefly at some detector data on I-66, for one of the earlier days, this was a Tuesday where we experienced a school closure, looking in the peak direction during the morning, on this graph, a negative number indicates that there was actually more traffic than our, say, 1.5 full weeks of undisrupted time, where we didn't have any holidays in January, we didn't have any delayed openings, and we didn't have a closure. So sometimes we had less traffic that would be indicated by a positive value, and sometimes we had more traffic indicated by a negative value. All right, so we have some changes that you see, and it's really hard to tell exactly what trend might be there. However, the PM is a little more easy to interpret. So in the PM, again, headed in the eastbound direction, we see that there's generally less traffic, lower volumes across most of the detectors. Okay, so that was earlier in the month. But then on that week where we had hardly any school at all, on Wednesday, January 22nd, you see, except for a couple instances here in the peak direction in the morning, we had large amounts of lower volumes, right? So say 70% reduction in travel, in vehicle volumes on certain detectors for the AM peak. So what we're getting from this in terms of the detector volumes alone is that it varies from winter event to winter event as to exactly how much volume reduction you should expect. Okay, and then in the afternoon on the same day there, we had all of the detectors showing a reduction in volumes over the non-winter weather disrupted days. Okay, so this suggests that based on even just looking at the detectors, that it would be hard to predict exactly what's going on if you're just going to look at detector volumes alone. So that gives us all the more reason to look at doing a winter weather survey. All right, so what we did was we conducted a survey for the Northern Virginia area, the Washington, D.C. metropolitan area, trying to ask people, what would they do under various types of weather and what changes they might make and how they rate the importance of different factors like their employer decisions and school decisions, how much they value road conditions and so on. So we ended up with about 418 responses. We did not limit this to commuters alone because we also asked about different types of travel, right? So we allowed people who are either working from home or that they are not working at all to answer our survey. Okay, and so again, we asked them what the commuters would do if the winter weather conditions began or were forecasted to begin while they were at work, and if the winter weather conditions began while they were at home. Okay, and then we took some of that data and started developing logit models, right, which were basically for binary choices, right? So we're looking for factors that are statistically associated with making a particular travel decision. And we started out by looking at each variable individually against the dependent variable for making a particular type of change. And we started with all the variables that were significant at the 0.25 level, and then we considered those in multivariable models. And then what we're going to present next is a set of those models. But first, a little bit on what some of the average responses were for the different types of weather. So for the cases where weather begins while the commuter is at work, again, we asked about these different types of weather events. So we had some snow, some freezing rain, heavy rain kind of as a control, temperatures below freezing, and icy roads. And so you can look at the mean here and see what was the average number of, or what was the average for the responses saying that they would make a change in their transportation plans. So for example, for snow events, over half of our sample who answered this question and were commuters would make a change. Okay, and so the least amount of changes made were related to heavy rain, which is what we expected. Okay, so the next set of slides are broken up into whether the weather event is going to begin while the commuter is at work or whether they're going to begin while they're at home. So the tables with the orange coloring pertain to all of the weather events that begin while the respondent is at work, and the yellow ones will pertain to the ones where they're staying at home, as you'll see in the future slides here. Okay, so you can see, again, we're just looking at the average and the number of respondents that we had for each of these different types of changes that could be made. And those include canceling a trip. Okay, so remember, this is while they're at home, so maybe they're canceling a discretionary trip or potentially even deciding to stay at work rather than to try and go home. We also looked at delaying a trip, leaving work early, adding trips, changing destinations, changing routes, using more highways, and changing modes. Okay, so in the first model, we're looking at the possibility of canceling a trip. And we see that we had basically a fair predictive power based on this model. The AUC, the area under the receiver operator curve, can give you an idea of how good for prediction your model will be. And we have the three variables that were important were whether the respondent self-classified as Hispanic, whether they had a teleworking option for winter weather, and whether they had child travel responsibilities for themselves. Okay, so for the first variable, the Hispanic variable, we can hypothesize that there are possibly fewer discretionary trips that would be available for them to cancel, and that's why they would be less likely to cancel a trip, and the less likely is indicated by the negative sign on the estimate of the parameter. So that's at minus 1.847. Or you can look at the odds ratio, which is in the second row, and that tells you that for those respondents who self-classified as Hispanic, they're about a tenth as likely to cancel a trip as other respondents. Okay, and for those who have a teleworking option, this implies some flexibility, but I don't have an exactly good reason why this variable was significant to the canceling a trip option. And then the child travel responsibility, it has the negative sign, means that they are less likely to cancel a trip. So we can suppose that the respondents with child travel responsibilities still have to pick up their children, right? So they can't cancel that child gathering trip because then they would be leaving the kids at daycare or so on. Okay, so the next change that people could make was changing their departure time to leaving earlier. Okay, this model had a fairly good predictive capability, and you see the variables that were significant here. So here we have the number of days that the people commute. We have whether a work policy allows absences to be excused. We have the age of the youngest child, and we have whether the respondent normally makes stops on their way home or not. Okay, so the first variable here, the commuting number of days, we find that more frequent commuters are more likely to leave early. And in the second variable, we have that the absences are excused. So this implies that people will not be penalized for missing some work, right, because of having this work policy in place. The age of the youngest child says that this is a continuous variable. So having an older youngest child increases the likelihood of leaving work early. So at first you may think that this is somewhat counterintuitive. However, if you think that very young children might be in daycare rather than schools, so it's possible that there's a little more flexibility in the winter weather policies of daycare centers compared to schools. And respondents who normally make stops during their commutes are almost 3 times as likely to leave work early as those who do not normally make those stops. And that might be explained by the respondents who normally make those stops to still plan to make those stops and need more time to complete the additional travel before the weather conditions become too difficult. In the next model, we're looking at whether people are going to make changes by adding trips. So potential trips that might be added, for example, are going to the store, gathering some supplies for potential couple of days when they're not able to go out because of the weather. Okay, we had respondents who self-classified themselves as Caucasian or white being less likely to add trips. We also had people who make leisure trips on a greater number of days being more likely to add trips to their commutes home when winter weather conditions begin at work. And perhaps these respondents are more comfortable with making these additional stops because they're accustomed to doing so. The next variable is the household size minus the number of adults. So there was some inconsistency in the responses based on household size and if you added a number of adults and number of children. So it created this variable that says we'll just take household size and subtract out the number of adults. So the households with more children increase the likelihood of adding trips to the commute. So it's potentially possible that the respondents with the more children have to stop to either pick up these children, even if they do not normally do so, or they may stop for items such as groceries, particularly if the weather is going to make it difficult to shop in the coming days. And then we also have employer decisions being very or somewhat important. Right, so that turned out to have some influence on these decisions. And then the final variable is that the road conditions were very or somewhat important. So respondents who consider the road conditions very or somewhat important may be more likely to add trips because they anticipate travel difficulties later. Okay, so the next set of models have to do with changing routes and the question of whether they would use more highways or not. So the model for changing route did not really have good predictive power, which is not too surprising because it didn't have too many variables in it. We just had the leisure number of days on which leisure trips are conducted, and that increased the likelihood of changing routes, perhaps due to the addition or subtraction of such trips. So if you don't have to make the same stops or you're making more stops, then you will have to change routes in order to include that stop in your trip. And then we also had that the family considerations were very or somewhat important. And potentially those respondents with family priorities would change routes to pick up children or spouses or to prepare for the weather, right, which would induce the changing of the routes. Then coming to the model for whether they would use more highways than they normally do, we have some fair predictive power with this model. We have, again, a set of variables here. The first one is whether leisure trips are conducted during the weekdays. So those conducting those leisure trips are more likely to use more highways when winter weather begins at work. So if those leisure trips are still conducted, the negative effect could be, so the leisure trips on the weekdays are less likely to use more highways, right, which is indicated by the negative value. And it's possible that because of the leisure trips, the destinations are not located on the highways themselves, and they may be more likely to follow their normal patterns. Then we also have the variable for whether respondents normally conduct errands on the weekends, right? So those who do their errands on the weekends are less likely to use more highways than those who do not conduct errands at all or do so just not on the weekends. And this could reflect familiarity and comfort with the use of local roads. Right? So they're more used to using those types of roads and feel comfortable doing so even in poor weather. So the next consideration here, we have respondents who normally use highways. So these people are more likely to use even more highways than normal. And again, this can reflect a familiarity and comfort with a particular type of road. Then the last variable is whether school decisions are very or somewhat important. Okay, and so for the respondents for whom those school decisions are very or somewhat important are less likely to use more highways than respondents for whom school decisions take on a lower importance. And this result should be relatively intuitive since schools are typically located on local roads and respondents may choose to pick up their children or simply follow normal travel patterns. So overall, from the use of the highways model, we're gaining some insight into the importance of familiarity with different types of roads and then their selection for winter weather conditions. And this is also a result that's reflected in many evacuation studies where we find that people are going to select routes in hurricane evacuation, for example, based on their familiarity with that route. Right? So across different weather conditions, we're seeing that this familiarity is a critical factor in people's decisions. Okay, and then the final model for when winter weather begins at work is related to whether people would change modes or not. And what we see here is that the model is not that great in predictive power, which is not really surprising since we only found one variable to be significant. And it has the variable is whether the mode of transportation normally used is the drive-alone mode. So a negative sign here indicates that for the people who are using their own personal vehicles, they're less likely to change modes. Okay, less likely than all other mode users. And, you know, having the negative intercept here also just kind of reflects what I'm calling inherent inertia in changing modes. Okay, so it's not really surprising that when winter weather begins at work, commuters have more limited options than when they begin at home, right? So they can't take a car home from work unless they brought one there, right? Or they could take a taxi, but then again, they're not the ones driving. Okay, and for considering the drive alone, that also reflects the potential comfort and convenience of the drive-alone mode. So in winter weather, it might be especially important to have a heated vehicle and to stay dry throughout the trip. Okay, and then if we move on to the considerations of when winter weather begins at home, say maybe the night before, the morning of. We had, again, a variety of potential changes, though I'm only going to show you the models for the ones that were more popular. Okay, so we had about 64% of our commuters said that they would cancel their commute. We had, again, a delayed commute early, add trips, change routes, use more highways, and change modes. Right? But it's interesting that very few people said they would actually change modes. Right, so looking at our model for canceling the commute. Again, the predictive power may be not that great, but still the variables can give us some important insights. So here we have whether people do not normally conduct errands at all. We have whether there's a flexible schedule option for winter weather. We have whether you can use earned leave for winter weather absences, and we have school decisions being somewhat important. Okay, so for those who do not conduct errands normally, they're less likely to cancel the commute. Okay, and potentially the reason for doing that is that they could be the sole source of the household employment and income. Okay, so they may have to go to work anyway. And then we have the two factors related to work policies, which allow people to cancel their commutes without any financial penalty. And then for the school decisions being somewhat important, okay, this is relative to those who consider school decisions either very important, somewhat, or not at all important. Okay, so for those that only have, it's compared to very important, mostly not important, and then not at all important. So for those who value school decisions only somewhat, they are less likely to cancel their commutes. Okay, so potentially those who have very high importance to the school decisions, they would be more likely than those who only assign a somewhat importance to the school decisions. So those who would be very important might be more likely than to actually stay at home and cancel their commute. Okay, then the next model is about commuting later, and this ended up having about a fair predictive power. We're reflecting variables related to the number of commute days, some employer flexibility options, employer decisions, school decisions, and child responsibilities. So we find that more frequent commuters are less likely to commute later. Potentially, these people will cancel the trip altogether or may be more likely to have flexible options available to them. Job flexibility, represented by our excused absences, also allows commuting later. So some of the employer options are correlated with each other. Okay, and then those who consider the employer decisions very or somewhat important are more likely to depart later. And it's also possible that employers will have delayed openings. And the school decisions being somewhat but not very important means that the commuters are less likely to leave later relative to those who would consider the school decisions not very important or not important at all. And then the last variable, those with the child care responsibilities would be less likely to commute later. Potentially, these people would have to remain home if the school is canceled altogether. Okay, so our commuting earlier model is not very strong in terms of predictive power, but we do have some implications that we can draw from the variables that were significant. So these variables, whether they commute on Saturdays and whether they have a flexible schedule option for winter weather, hint at maybe the type of work that our respondents have, right, and the need to be there on time. So in this model, we see that the Saturday commuters are more likely to depart earlier, and those who have flexible schedules will be less likely to depart earlier. Okay, so these variables make sense, and the effects make sense. And if you relate it to whether you have to be there on time, then you'll be likely to allow more time for your commute during winter weather. Okay, our next model is about changing routes. Again, this model is not particularly strong in terms of predictive power, but still the variables are making sense and giving us some insights. So we have the flexible schedule variable showing up again, and it's possible that they're taking on other travel or stops, and possibly they have the ability to take some time to experiment with routes, which increases their likelihood of changing routes over people who did not have flexible schedules. The mode drive alone naturally allows greater flexibility in changing routes than someone who's taking transit. And then we also have the number of days on which errands are performed. So the greater numbers of days on which errands are performed implies greater flexibility and familiarity with local roads and alternate routes. So they may be more comfortable with a greater variety of roads, and that could encourage them to change routes. Okay, so the final model here is about using more highways when winter weather begins at work. And we have pretty good predictive power here, as you see with the AUC value of 0.8. Right. So here our variables include conducting leisure trips on weekdays. So these people are less likely to use more highways, and it also implies familiarity with the local roads and perhaps comfort with those roads over highways. The employer, for those respondents whose employers' decisions were somewhat important, they are more likely to use more highways. Those normally using local roads are less likely to use more highways. Again, this implies comfort with the local roads compared to the highways. Those who have teleworking options during winter weather are more likely to use highways, and perhaps these people have to commute for longer distances, so the highways could make more sense for them. The road conditions being very or somewhat important was causing people to be more likely to use highways. And it could be that highways are perceived to have better plowing or conditions than local roads during winter weather. And finally, we have that the school decisions were very or somewhat important, having a negative effect on using more highways. Again, just like in the model for when we had winter weather beginning while the respondent is at work, the schools are not located on the highways generally. They're located on local roads. So again, people who are going to have kids and travel to the schools, they're going to be potentially more comfortable with the local roads than they are with the highways. Okay, so some of the conclusions that we're able to draw from this study are that the different decisions are associated with different factors, right? So the different sets of changes that are made are all influenced by different variables. So we didn't find any variables that were consistent across all of our models. So that's significant in and of itself, and says that you can't just pick one variable and say, well, if we know this, and if we know the value for this variable, then we can get a good estimate of what's going, all the different changes. It's just not going to work. And then other conclusions are that we need to understand the personal considerations and constraints that are varied and complex. So we need to understand family situations, school and employer decisions, whether people have job flexibility, and their normal travel behavior. So what we saw, particularly from the use of the highway models, is that the comfort and familiarity with different types of roads could be an extremely important factor as to whether we should expect greater or lower volumes on the freeways. Okay, and so Nazi, of course, sponsored this work, but they're not responsible for any of the views presented here. I have pictures of my kids. You can see we had quite a substantial amount of snow. It's like up to their waists this past year. And I guess, should we do the poll question first before we do the opening it for questions? Okay, so my question to you then for the poll is, do you think that having a better understanding of individuals' travel behavior changes would lead to changes in winter weather road treatment procedures? Okay, great. Those results make me happy. I guess, are there any questions that you guys have for me on the material in the presentation?
Thank you. So if everyone has any questions, please type into the using the chat box on the left. Dr. Rakha, if you want to, you can use this as well if you want to talk.
Okay, we have a question about whether the survey included any public transportation users or only car users. And yes, we did public transportation users in the survey, although the proportion was fairly small. So we still have some model development and testing to do, and so we'll look at some statistical differences between car users and transit users as well. So,
hi Pam, this is Hesham. I had a question. I guess given the low explanatory power of the models, could we just use constant reduction factors to capture these behavior without having to go into having to collect all these parameters on the person who is embarking on that trip?
well, some of the models were good, some were not. So not all of them were bad. But when we looked at the detector volumes, if we go all the way back to the beginning, it's hard to say that you could just do a constant reduction factor because it really depends on the context, right? So the 1 week on the 7th, you see that we have some detectors showing reductions and some showing increases, right? But on the week, the next week that we had a lot of, almost the entire week closed, it was more consistent about the reductions. So even just looking at the detector volume shows that we're running into some complexities, potentially based on the number of closures we've already had. And, it's really hard to say whether that would work, just using a constant reduction factor.
But I guess from your models, it seems that there'll be more people shifting towards the highway, but there'll be, I guess, people will be canceling their trips or delaying their trips. So you've got some factors pulling them away from the highway and some factors pulling them towards the highway. So you've got two pulling forces. Is that correct?
Yes, but some of them are working in opposite directions. Yeah.
So a good check would be to run your models and compare it. If you ran your models and estimated the flows on the highways, how do they compare to what you observed from the loop detectors?
Right, and that's one of the things that we still want to do. We haven't had time to get that done. Another question from the list here was a similar survey implemented in New York City, where there's a population of people who commute by public transit. So my understanding is that MAUTSI would prefer to fund studies that are conducted in the area that they cover. And as far as Washington, D.C. is considered, Northern Virginia will often commute to Washington, D.C., so we were capturing some of the D.C. folks. We do have a study that we conducted for Hurricane Sandy, which focused on New York City, and that looked at some of the changes that they make. So we haven't done a comparative study of hurricane and winter weather in particular, but we can do that in the future.
So if there's no more questions, we're moving on to the next presentation.
Okay,
I can
thank
see
you
someone
very much.
typing. Thank you, Dr. Pam. Okay. So we have John Stankster and Dr. Hesham Rakha here for the next presentation. So I will let them start.
This is John Sangster here in Blacksburg. We have Dr. Rakha in the room, but he's passing over the torch to me to present this information. So we are going to do, if you bear with us, we're going to work with technology today, and we're going to share our screen. Might take us a second to bring it up here. We did a dry run with the video and determined that we need to jump through some hoops. All right. We do have a laptop available here where we can see the chat box. If you're having problems hearing, or if you're having problems with sharing the screen, if you're not seeing what's going on right now, you should be seeing a picture of the front of our slide deck. So today I'm going to talk about alternative intersections. Our research is focused on analysis methods, but we do have a little bit of bias. Our goal is making the analysis easier to conduct and transitioning these more from the category of alternative intersections towards just regular intersection alternatives, things that are considered every day. We had a bit of a survey earlier about familiarity. It looked like most people had encountered them. A couple people had done some research with them. I will put you on the spot, and for our first poll, we've got 6 intersections here. I'll give you one for free. The top left is a conventional T intersection. But if you can take a look at the geometries and just as a poll, let me know how many you can name. There's no extra points for telling me what city the pictures are from. Here we got the poll coming up. Okay, so the request is to have the numbers reported instead of in a poll in the chat box on the left side. All right, well, I've got about 40 minutes left in our webinar today, and I've got 40 slides to work through, so I'm going to jump ahead. The responses are that we've got the conventional T intersection in the top left, the modern roundabout design in the middle, and if you're looking at the pictures, the buildings on the top left and the middle are the same buildings, just different times, out of interest sake. The top right is a jug handle design. It's an at-grade intersection. And on the bottom, we've got, on the bottom left is the restricted crossing U-turn with the median U-turn location in the middle. And similar to the top picture, those pictures overlap. In this case, they're adjacent intersections. And then the bottom right design is a partial displaced left turn. For the many in the crowd that are not as familiar with these, I'm going to go quickly through them. So here's the reason why we're doing the picture-in-picture sharing screen. We've got the little cars in the video. These are videos that the University of Maryland developed, maybe a decade now ago, that I find really useful when I'm teaching this material. So the jug handle intersection is popular in New Jersey. You're prohibiting on the main arterial left turns and forcing those left turns to go around either with an upstream kick off to the side, or they go past it and come back around with a loop. The video is showing that upstream little jug, and the image on the right side is showing where they go past it and loop back around. The next design we're talking about is the median U-turn. In this case, you're prohibiting either the left turns from the main arterial or left turns in both directions at the intersection. You're cutting down the phases in this way, and you're forcing everyone to go down and use the U-turn that's located about 600 feet or so up downstream and come back around. The restricted crossing U-turn is a variation on the median U-turn. In this case, we're allowing left turns at the main arterial, but we're prohibiting all left and through movements from the side arterial. In this way, we're acknowledging a location where there's a high volume of left turns, but a low volume of the minor street. We still need to provide access. We can maintain our throughput on the main arterial and allow that access from the side street in this way. And lastly is the just partial displaced left turn on the right. It's a picture from Colorado. And in the video here, we have the full displaced left turn. This is the one that people who are unfamiliar with alternatives generally have the biggest problem with. I had the pleasure of presenting this material as part of a lecture to about 200 sophomores last week, and the room started with some chatter when the video started playing, and then it grew to giggles and then outright laughter after about 30 seconds or so. So there is some hesitation as people first come to these. In this case, we are prohibiting left turns at the main intersection again. We are providing upstream crossovers for the left turning vehicles. We're bringing them over to the opposing side of traffic. And then once they get to that main intersection, we're allowing the lefts and the throughs to use the same phase of the signal. This works really well when you've got similar volumes of through and lefts in terms of a per lane volume that are seeking to make those movements. It allows you to cut down the phases and allow everyone to go to conflict. And finally, I think at this point, everyone's well familiar with the modern roundabout. Give you an example here in Virginia. The first one in Virginia was built in 2004, and by 2008, the DOT changed the road design manual to say that in a location where the modern roundabout works, it is a preferred design from the DOT's perspective. So that's very quick turnaround from my perspective. The image on the left, instead of the video, I'm sharing an aerial image from Malta, New York, where they actually have, I believe it's 6 roundabouts in a corridor, one after another at this point. So the next poll of the day asks about your comfort level with these. We're looking at a number 1 would indicate you wouldn't recommend this design, you're not comfortable with it, and a 5 would indicate that you're thinking this might solve a problem that you've encountered, and that's something you'd recommend to your client. So an anecdote while you're responding to these, in that sophomore class, of what 200 students, I asked them afterwards how many would recommend the displaced left turn intersection to their client. And I had about 3 people out of 200 raise their hand. And I left them with the thought of how many people would recommend it if it cost $3 million to build the displaced left turn, but an interchange option cost $10 million. Would they be more open to it at that point? All right, so the jug handle has actually got some fairly consistent okay responses. We've got some resistance, some strong resistance to the, oh, no, I take it back, some strong approval of the roundabout. That's very different than we would have seen 5 or 10 years ago. And some fairly good approval for the other ones as well. I think we're probably pulling from a crowd that's more agreeable to these designs. All right, if I switch back to the PowerPoint. Okay. All right, so design with a purpose. We didn't develop these designs because we're sadistic and we don't like the average driver. We developed them because they do serve a purpose. In this case, we're talking about conflict. The conflict is causing accidents, causing fatalities, and it's also causing delay as we use signal control to separate those conflicts. So at the conventional intersection, we're looking at 16 crossing conflicts. Those are the most dangerous. They result in T-bone collisions. That's where people get killed. And we've got 8 diverging and 8 merging. The reason the roundabout is so popular is because we completely get rid of those crossing conflicts and we leave ourselves with just 4 merging and 4 diverging. And this is a simplified 1 lane on each approach. But either way, it really drives home the safety measures of the roundabout. Lots of accidents still happen at roundabouts. People are still adjusting to them as they encounter them afresh. But when accidents do happen, it's more property damage and a lot less fatalities, a lot less injuries with these designs. At a conventional intersection, we're controlling that conflict. We're trying to prevent people from getting injured. Here's an example, the ring and barrier design separates those conflicts into different stages of the signal. This is great for controlling conflict. It makes sure that people are going only when they're not being opposed, but it introduces a fair amount of time throughout the cycle where no one's moving at a given point in time. Examining all the different designs, we can see varying levels of reduction in total conflicts. All of them reduce those crossing conflicts. And in this case, we're doing a trade-off between conflict and travel distance. So my main approach is not on the safety side of things at this time. I'm looking at the operational analysis, and I'm trying to analyze the existing methods that we have available and how to make them better. So for analyzing intersections, we've got capacity-based methods for preliminary design. We have engineering design at the macroscopic level. We've got trans, traffic aware, PTV, all providing applications of the highway capacity manual method or similar methods. And then as we move into the research side of things, we're looking at microscopic delay-based microsimulation. I say research analysis in this case because we're only talking about at-grade intersections. Once you go to grade separation, most consultants at that point are going to have access to simulation software. The problem with alternative intersections is when we try to do comparative analysis, we no longer have those engineering design softwares. They are coming. The Federal Highway is currently funding a couple of these designs for implementation in the next round of the Highway Capacity Manual. Once it's in there, it's going to make its way very quickly into these software packages. But for right now, all we're left with for analyzing these intersections, if we need to use them to solve a problem, is the capacity-based analysis for preliminary design, and then full microsimulation to get the final result. So this capacity-based analysis, proposed in the early 70s as a layman's understanding for signal control, it actually has subsequently been used as the underpinning, whether you call it critical sum method or critical lane analysis, it's the underpinning of the highway capacity manual method. And it looks at the number of vehicles per lane on each approach and trying to determine which one is governing the phase length of the cycle to determine what our ultimate capacity is at the intersection. So our first check in our research was examining how the capacity measure with critical sum related back to the highway capacity manual method. Is this an indicator variable that's giving us results that are dependable? We took 3 different sizes of conventional signalized intersection. We fed a whole bunch of different volume combinations into them, and we checked the critical sum values that were calculated against the delay measures. And we found that the curve between capacity and delay was fairly consistent, fairly reliable for conventional intersections. So based on the initial findings with conventional intersections, how comfortable do you feel with capacity-based analysis in general? Would you use this to design your intersection outright? Is it a tight enough relationship that you feel comfortable going with design? Or would you use this instead to choose alternatives? If you select 3 out of a group of 7 designs, how confident would you be in that? And the scale we're looking at is 1, I would not recommend this, and 5, this seems like a good idea. Okay, we've got a fair number of people who are comfortable with using the capacity method for design. Maybe split evenly. There's no strong feelings on that one, which kind of surprises me. And then many people are very comfortable with using this to choose a subset of alternatives. That's kind of what I expected to start with. All right, I'm going to switch back to the PowerPoint. I'm having trouble on this end. You are not seeing it when I pull it up. Okay, so here's a technology glitch. I do not have that button that says share my screen. Let me try show that. Should I log back into this?
Yeah.
Okay. Bear with us for a minute. We were hoping we wouldn't encounter this. All right, sorry for the technical difficulties. Okay, so we've got this capacity method. It's a set of equations. It's very easily implemented in Excel. That's how Federal Highway has developed their software. This gives us the additional option of running hundreds of thousands of volume combinations through it for each design and saying, okay, if we're going to take this method at its word, what conclusions can we draw from it? So I ran about 300,000 volume combinations through 3 different sizes of each of 6 different alternative designs. Pulling the critical sum values out of that, the 1600 line is kind of where a standard definition of capacity is reached. So I'm saying anything in the 17 and 1900 range, I'm confident is failing, and anything in the 1300 to 1500 range, I'm confident is a volume combination that's going to work. Trying to understand how to relate this information out to practitioners, I came upon the MUTCD signal warrant charts as an axis where I could convert my information to make it make sense. Here's some examples of the 6 designs, the different sizes I compared them at, both looking at smaller designs and larger designs. From a research standpoint, we tried to develop equivalent intersections for each design, and in terms of that, we had to use some basis. We looked at number of lanes approaching and leaving each side, and we looked at total impervious area of each design, trying to get a feel for which one is equivalent to, how many lanes is equivalent on this design to that design. From there, using the critical sum method, we were able to draw conclusions about the failure thresholds of various designs. We actually found that the conventional signalized intersection is relatively robust based on the critical sum analysis. And the displaced left turn is the most robust, and the roundabout by far serviced the least different volume combinations before it reached failure. So if you're looking to do this type of analysis, you've got a situation in the field where you've got volume counts, and you want to look at, instead of doing grade separation, you want to look at different alternatives. You want to see approximately how many lanes you're going to need to solve your problem. Federal Highway has developed this tool that implements critical sum analysis called CapEx. You can Google it, you can download it, it's free, it's available, it runs in Excel as a series of tabs. It has a very simplified input screen. It provides a diagram of each intersection design. The lane configuration does not update as you change the number of lanes that you're using for your design, but down below each lane configuration diagram is a very simple method for updating how many lanes you're providing to each approach. That'll give you a readout of the critical sum value based on the lane configuration that you've entered and the volume demands that you've put in. In this way, you can simply and quickly design different layouts, see if adding that extra right turn lane will really solve your problem. It's a good tool when you're sitting down with a client for a meeting and you want to solve their problem. It gives them something visual to focus on. The end result is on a different tab within the Excel spreadsheet and gives you a color-coded reference point for the various designs based on the configuration, number of lanes that you've input into them, and which ones are predicted relative to that 1600 critical value to be working well. I have to preface at this point, it only tells a small part of the story. The site constraints for these designs will govern in a lot of cases. If you don't have the right-of-way you need, if you don't have a boulevard, you're going to be governed by that more than what you'd like to do. In some cases, some traffic movements are more important than others. Those major arterial lefts might be more important than the minor arterial, or vice versa. And the relative cost of each equivalent design, you can figure out what you need to build out, but that doesn't tell you which is the most cost-effective solution. And the ultimate question that I'm trying to answer is the analysis actually predicting relative performance that we're going to see in the field? Another feedback poll. Do you feel that this tool is appropriate for use in industry applications or as a teaching tool? And we've got 1 means I would not recommend this, and 5. This seems like a good idea. Okay, fairly even results on using this in consulting. Consistent results on liking this as a teaching tool. I've used it in the classroom. It's worked fairly well for me, especially in teaching signal control and understanding how we lay out designs and how we're meeting our traffic demands. All right, I am at slide 29, so I'm going to keep on going. All right, no technology glitches that time. Sorry about the previous time. All right, so we've got this capacity analysis. We have a tool that makes it very easy to use. We want to know, though, is it giving us the results that we think it is? When we look at that color-coded solution, is that really what we're dealing with? We tied capacity to delay for the conventional signal noise intersection, but we've made at least too many assumptions. The first assumption we made was that the critical sum value representing failure is equal for all intersection geometries. The definition of failure from the high capacity manual is the maximum number of vehicles that can pass through a facility within a given hour, or can reasonably pass through a facility within a given hour. That's a little bit loose of a definition, and I'll get back to why that matters in a minute, but what is the relationship between critical sum value and the average delay? That curve that we looked at for the calibrated conventional signal is the same curve found for each of these other designs. If you're talking about a critical sum value of 1300, does that mean 50 seconds of delay for every design, or does it mean different values for each design? Because that's going to make a huge impact on which ones you move forward with. So in this case, we have to use microsimulation. We have to abandon that 300,000 volume combinations, not an option anymore. So we're going to start holding most of our parameters constant in terms of turn percentages, things like that, and start doing sensitivity analysis on overall volume, or on percentage of left turners, or on directional split. If we look at different conditions and do some sensitivity analysis on that, holding of that travel time versus delay question. If we use simulation and measure control delay as the difference between the speed the vehicle's traveling and the speed it wants to go at, the gray bar on each design is showing you the control delay. The black is a measure of the additional travel time that a given movement needs to make at that design as it passes through. So we can't just use control delay when we're analyzing these intersections. It's not going to give you an accurate representation of performance. We need to use travel time in some capacity and then tie that back to delay. Moving forward, this winter, our research is still ongoing. We're going to look at delay and capacity interactions for multiple sizes of each design, make sure that the relationships we found for the initial size holds true. We're going to look at a wider variety of volume combinations, vary the left turn percentage, vary the directional split, and if it's appropriate, we're going to develop translation equations so we can convert those capacity measures back to delay for each design. If I'm giving you a consistent set of this capacity for this design equals a given delay, we can then go back to CapEx and we can incorporate these translational equations so that the comparative analysis it's providing is actually going to lead to results when you run simulation where your delay is going to be consistent with the relative performance that capacity is predicting. And moving forward, we also like to keep broadening the volume scenarios. These designs each have their own quirks, places where they don't work as well, places where they work better, and it would be of value to identify those. Future outlook, signal optimization and coordination of these intersections is really a huge factor in their success. If you're not coordinating them properly, you're going to get vastly different results than you're expecting. And from the research perspective, as electric vehicles become more common in the vehicle pool, our delay time is not going to be causing fuel consumption, fuel emissions, and the number of stops might become more critical issue than the total measure of delay. These intersections might become more advantageous once the measures we're using switch over to represent that future vehicle pool. If you're looking for more information on alternative intersections, if I piqued your interest, Federal Highway has the Alternative Intersections and Interchanges Informational Report. That was released in 2009. I know there's a draft right now of an update to that report. I don't believe it's available to the public right now. I was able to give a TEDx presentation at Virginia Tech in 2012 on this topic. If you want to share this information with non-practitioners, with people outside of transportation, but these designs might give them a chuckle, that's a pretty good presentation for that purpose. And also, if you Google the Alternative Intersections and Interchanges Symposium from this past summer, the slide decks along with the audio are available online. There's a 4-day conference in Salt Lake City. There's a whole host of presentations on all variety of topics there. And with that, I'll wrap up with my final poll. Based on this presentation, do you now feel more or less comfortable with alternative intersection geometries or the analysis of alternative geometries? A 1 means that I made you feel less comfortable with these designs, or I made you feel less comfortable with analyzing these designs, and a 5 means I made an argument for comfort.
You mean in terms of knowledge or documenting them or using them?
Yeah, so the question is whether you feel more comfortable that you choose these designs, or whether you just feel more comfortable understanding them to attempt using them if you needed to. All right, we're switching back to... All right, my last slide just says questions, and I had the same technical problem I had before, so I'll open the floor at this point to questions. I don't know. Questions? So the first question was, do you know any public acceptance study results of alternative intersections? Oh, we got a feedback loop here. All right, we're back. There was a paper on this that was published. I think it's in like Public Works Journal or something like that. It's a Joe Harmer publication, and it's a survey of I believe it's practitioners and their comfort levels with these designs. That's about 4 years old now. I don't know if that's current enough to make sense with the changing landscape as people are accepting modern roundabouts or not. That is out there. And the safety study on these results is a tough call. Most of these designs, with the exception of a couple that have been around for a while, have not been implemented frequently enough or for long enough to get that 5-year before and 5-year after safety results that you need for a solid safety analysis. There's an expectation that reducing and separating the conflict points are going to result in improvements in safety, but at the same time, if you're increasing the travel time, there's a certain percentage of accidents for, per mile of travel. So at that point, you're increasing your risk. So there's a trade-off there. Second question. Okay, so the second question is, when using microsimulation, did we adjust the gap acceptance effects? And the simple answer at this point is that we did not. I think the more nuanced answer is that the simulation software we were using does not model the behavior at the intersection node itself, and that gap acceptance at like a median U-turn, for instance, at the U-turn location, the gap acceptance, as far as I know, has been seen to be about the same, follow similar patterns to gap acceptance for a right turner or a left turner that's permitted. In most cases in our simulation, we had protected turns, both at the main intersection and at the U-turn location. So gap acceptance would have come up less of it as an issue. Any other questions at this time?